We have already studied atoms in quite a lot of detail. We've looked at their protons, their neutrons, their electrons. We've looked at what happens when they become ions. But the point is that atoms very seldom exist all by themselves. Most of the time, atoms are in some sort of a bonded compound. And we are now going to take a look at why atoms are going to bond. Now, the reason they bond is to lower their energy. That is the key reason for bonding. And they lower their energy by becoming as similar to a noble gas as possible. And we'll look at that in a little bit more detail in a second. But as you know, the noble gases have usually got 8 valence electrons, or in the case of helium, 2. If atoms are going to bond, they need to first collide with one another. I often liken this to human beings. So you've got two people, they're going to meet each other. They need to, in order to meet each other, they need to first say hello. They can't say hello with their backs towards each other. They need to face each other and they need to say hello, facing one another. And then there's a chance that they might like each other and go off as friends. But there's also a chance that they say hello and move on in their separate ways. But in order to bond, the first thing that has to happen is a collision between the atoms. Electrons then are either shared by the atoms, or they are transferred. Well, the first thing is that they may just walk off in the opposite directions. But in order to bond, these two guys say, hey, should we share some electrons or should we transfer our electrons to one another? And it all depends on who's stronger and weaker in terms of something called electronegativity. We'll talk about that in a minute. So the bonding itself is about the sharing or the transferring of electrons. You know from earlier on in the year that we had valence electrons. That was how many electrons are in the outer energy level. Let's just remind ourselves of that. So valence electrons are the number of electrons in the outer energy level. So group 1, 1, group 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 6, 7, 7, 8, 8. Then there's something called valency, which is fractionally different. And we learned about it a lot last year. That was the number of arms. But it's not really just the number of arms. It is more clearly defined as the number of electrons that participate in bonding. So again, this boils down to the electrons. We simplified it last year. We simplified it when we wrote molecules earlier. And the valency is the number of electrons that participate in bonding. But it's just like the arms that we would draw. There are attractive forces when a bond occurs, and repulsive forces when a bond occurs. Now, you can think of this as any relationship between human beings. There are parts of the human being you think are amazing, and other parts of the human being that you don't think are so amazing, but you still stay friends with them, because overall the attractive forces are greater than the repulsive forces. When a bond is formed, energy is released. And then when I break a bond, energy is required or taken in. So you have got energy changes that take place when bonds are made and broken. Very important, forming bonds releases energy, whilst breaking bonds requires energy. These two energies have different names. The bond energy is defined as the amount of energy given off when 1 mole of molecule is formed. Bond energy is negative because it is released. So that is energy given off. We'll talk about that in a bit more detail next year. Dissociation energy is the amount of energy required. In other words, it is energy that is required to break up 1 mole of a molecule. Dissociation energy is positive and it is taken in. Now, it has exactly the same value as the bond energy, but it's a different sign. So if I say a bond energy of hydrogen is negative 435, that means 435 kilojoules was released when I made hydrogen. Then the dissociation energy, in other words, if I want to break hydrogen into its parts, is equal to 435 with a positive. That's the energy required if I would like to break up hydrogen. As scientists, we like to graph information. So this story starts, the x-axis is the distance between the nuclei, the y-axis is the potential difference. So here the nuclei are far apart, big distance between them. Here they're very close together, small distance between them. So what happens is we often read this graph almost from right to left, which seems a little bit strange. Because why don't we just draw it the other way? Because remember, when the distance is big, we're going to land up with being on the far right of the x-axis. So you start off with your two atoms so far apart that they don't know each other at all. They have what we at that point assign them an arbitrary value of 0 energy. As they come closer and closer together, they are going to lower their energy. They release energy as they bond. So as they get closer and closer together, the energy gets lower and lower and lower until some beautiful point where they are exactly the right distance apart. Now, when human beings meet each other, they are comfortable talking to each other when they are about, let's say, 1 meter apart. If they get any closer to each other, they feel uncomfortable. So if you want to have a conversation, standing 10 meters apart is too far. You get closer and closer and closer until you get the right bonding distance, the right distance for a conversation, and that is a lower energy value. And then eventually you can push too close together and then it becomes uncomfortable. So atoms are far away from one another. We give them an arbitrary value of 0 potential energy. As they approach, the attractive forces cause the potential energy to become lower and lower and lower. The potential energy reaches a minimum, which is the distance of the perfectly bonded molecule, and that is stable. It is most stable at the lowest energy point. If the nuclei of the two atoms are forced any closer together, the repulsive forces become overwhelming and they sharply increase. This is an unstable situation and it does not occur naturally. Naturally, they will stop at the comfortable bonded stage. So, when two atoms are held together by strong electrostatic forces now, electrostatic forces have got some synonyms. These are just the attraction between positive and negative attractions, or the repulsion between two positives, or the repulsion between two negatives. Those are all electrostatic forces, also known as Coulombic forces. Same thing. Only the outer electrons, the valence electrons, will participate in bonding. The middle electrons, and when we did the atom, we looked at it in a great deal of detail. The core electrons are in the inner energy levels, and they do not participate in bonding. What happens when a bond occurs? The valence electrons are going to overlap in what we call molecular orbitals. Now, up till now, we looked at s orbitals and p orbitals. Now, you don't have to know shapes or their names, but you just need to know that once a molecule forms, there are regions of space where those electrons will live. So a molecular orbital is simply the region of space where the shared electrons live. Bonded atoms are known as molecules. You've learned this since you were in grade 7 at least, or unit cells when they form compounds. We'll talk about this unit cell a little bit later. For the moment, you can worry about atoms joined to form molecules. Molecules are completely different to the elements that make them up. And I'm going to remind you of two stories that I've told you in the past. The first is we have something called sodium. Sodium was that soft metal, and it you can cut it, and when you put it into water, it sizzles around. You add that to a substance called chlorine. Chlorine is mustard gas and is poisonous, and you get something called sodium chloride, which is a white powder that sits on your table when you are eating, and you eat it all the time. Completely different compound to the elements that made it up. And the same is true. Hydrogen is an explosive gas. You know that from the test for hydrogen. Oxygen is a gas that is highly flammable. You know that from the test for oxygen. And they go into some sort of a liquid that puts out fires, which is very, very convenient. But again, the compound is completely different from the elements that make it up. So let's look at a noble gas structure. You've seen this before. Helium has 2 electrons in its outer energy level. Neon has 8. And argon is sitting over here with 8 electrons in its outer energy level. And these are your core electrons, valence electrons. Core electrons, valence electrons. In the case of helium and hydrogen, the core electrons are the valence electrons. What's important over here is that the electrons are always paired in a stable situation. They have very low energy in the noble gas, and that's what everybody's striving to be, a noble gas. If you look at your periodic table and you think about how we've written formulas, fluorine would like to become like neon. Sulfur would like to become like argon. Sodium would like to lose 1 electron and become like neon. Calcium wants to lose 2 electrons and become like argon. So there's always this whole thing about them wanting to be like their nearest noble gases. The noble gases do not participate in bonding at all. Right, now, there's another number we need to look at on this periodic table. It is called the electronegativity. It's this number over here, and it tells us it is the tendency of an atom to attract a shared electron pair in a bond. We'll look at that definition a whole lot more in a short while. And now what you need to do is you need to take a look at what does that number mean. The biggest electronegativity on the table is 4. And the smallest, well, you don't have them, but the smallest we're going to worry about is down here at 0,8. So it's a pretty tight scale because it goes like from 0 to 4. Some of these ones have got even lower electronegativities. Let's think about it. Fluorine over here would love to gain an electron to become like neon. It attracts electrons very strongly, 4. Sodium over here really wants to get rid of one of its electrons to become like neon, so it hardly attracts electrons at all, 0,9. Sulfur attracts quite well at 2.5. Now what happens is whenever elements bond, they come together with their electrons. Let's take our sodium at 0,9 and let's bond it to chlorine. Man, I want to seal there. Chlorine at 3,0. These guys set up a tug of war over the shared electrons. Who's going to win that tug of war? Well, chlorine's much stronger in terms of electron attraction than sodium. So those electrons go to the chlorine. And the chlorine becomes negative and the sodium becomes positive. Chlorine has got the one extra electron it wanted to become like argon, and sodium has lost its electron and has become like neon. So this electronegativity tells us who's going to win the battle over the electrons. I'll do another example. Let's look at water. Hydrogen and oxygen's at 3.5. Hydrogen's 2,1 and oxygen is 3,5. I'm just going to look over here. The electronegativity difference between these two was 2,1. That's quite a big difference. The electronegativity difference over here is only 1,4. That means that this hydrogen and oxygen, the oxygen is going to win those electrons, but not as convincingly as chlorine won these electrons, because the electronegativity difference is lower. In other words, there isn't as big a whitewash strength difference between the two elements as there was over there. We'll look at that in quite a lot more detail in a minute, so you're going to need to focus on this number called electronegativity. Electronegativity is defined as the tendency of an atom to attract a shared electron pair in a bond. Non-metals have got high electronegativity, metals had low electronegativity. You saw that on the table. The noble gases don't have electronegativity because they don't bond. In bonding, we often look at the electronegativity difference, and I want you to look at the scale carefully. When I look at the difference in electronegativities, you have what's called a percentage ionic. In other words, how much does that electron go to the other guy? When there's hardly any difference, the percentage that one or the other of the atoms takes the electron, so this percentage ionic is that one atom gains that electron. In other words, it takes full control of the electron. Doesn't happen when there's a very small difference of electronegativity. Eventually, at around about 1.7, there's a 51% change in electronegativity, at least percentage ionic, and then we often just say that the electron was transferred. Whilst over here, the electron was shared. And we'll talk about this in quite a lot more detail, but what I want you to see from this scale is that it's a gradual scale. As the electronegativity difference slowly gets greater and greater and greater, so the percentage of ionicness slowly gets greater and greater. There's no clear one way or another way. It's like a rainbow. It's a gradual change.